So good morning to one another present here. Today we will discuss about the topic in the one-dimensional bar element. Okay, see the one-dimensional bar element. Consider a bar as shown in figure. Okay, so this is the one-dimensional bar element. Okay, is shown in figure. An axial load of 200 kilonewtons applied at the point P. Okay, see this is the point P. In this point we have to apply the load of 200 kilonewton. And the area of element A1, okay, this is the element 1 and this is the element 2, okay. Element A1, the area is 2400 mm square and the Young's modulus for the element 1 is 70 into 10 power 9 Newton per meter square is given in the sum. As this see the area 2, okay, so second element, for the second element the area 2 is 600 mm square and the Young's modulus for the element 2 is 200 into 10 power 9 Newton per meter square. Okay, so what you have to find out means you have to find out the nodal displacement at the point P. What is the displacement at the point P and what is the stress in each material? Okay, so what is that element 1, what is the stress, and element 2, what is the stress? You have to identify this, and you have to identify the reactional force. Okay, what is the reactional force at the in the element 1, and you have to find out the reaction force at the element 2. Okay, so these are the things you have to find out from the sum. Okay, and let's see here one by one. Okay, so this is the given sum. Okay, so this is a one-dimensional bar element. Okay, this is the bar element. This is the element 1 and this is the element 2. The element 1 is located between the nodal point 1 and nodal point 2. The element 2 is located between the nodal point 2 and nodal point 3. The length of the element 1 is 300 mm and the length of the element 2 is 400 mm. Okay, so you have to find out the nodal displacement at the point P, stress in each material, and reaction force. Okay, so for the area of the element A1 is 2400 mm square. For the area of the element 2 is 600 mm square. The length of the element 1 is 300 mm. The length of the element 2 is 400 mm. Okay, is already given in the sum. The Young's modulus for the material element 1 is 70 into 10 power 9 Newton per meter square. You have to convert this unit conversion, because for the element A1 and A2 are mm square and the length also in mm only. Okay, that's why you have to change the units from Newton per meter square to Newton per mm square. For the element Young's modulus for the element 1 is 70 into 10 power 3 Newton per mm square. You have to convert this Newton per meter square into Newton per mm square means, okay, so you have to 10 power minus 6, okay, already is 10 power minus 3, 10 power 9 into 10 power minus 3 is almost 10 power 3. Okay, so element for the element 2, that is 200 into 10 power 9 Newton per meter square. You have to convert to Newton per mm square. That is 200 into 10 power 3 Newton per mm square. Okay, so the point load for the point P is 200 into 10 power 3 Newton. Okay, this is the load is acting, okay, at the point P. Okay, at the nodal point 2. Okay, so first you have to find out the element 1. Okay, first you have to find out the stiffness matrix for the element 1. Okay, this is a global stiffness matrix. Okay, that is a global assembly matrix for the element 1. Okay, that is F1 F2 that is equal to K into U. This is the formula. That is force matrix. Okay, that is force matrix that is equal to K matrix. Okay, K is nothing but stiffness matrix. Okay, into displacement. Okay, into displacement. Okay, so this is the thing. Okay, for the element 1, see here, this is the element 1. The element 1 is located between the nodal point 1 and 2. Therefore, you have to convert the assemble the matrix like it F1 and F2. Okay, the stiffness matrix. Okay, one-dimensional bar element. The stiffness matrix formula is AE by L 1 minus 1 minus 1 1. Okay, this is the formula for the stiffness matrix for one-dimensional element. Okay, and the displacement at the for the element 1 is U1 and U2. Okay, so this is the global matrix. Okay, that is a global force matrix for this bar element. Okay, so let's see here F1 F2 and that is equal to A1 E1 by L1 1 minus 1 minus 1 1 into U1 U2. Okay, therefore F1 F2 that is equal to the area for the element 1 is 2400. For Young's modulus is 70 into 10 power 3 and length is 300. Okay, so 1 minus 1 minus 1 1 and the displacement is you have to take as U1 and U2. Okay, so F1 F2 you have to solve this calculation and finally you have to find out the 1 into 10 power 5 that is equal to 5.6 minus 5.6 minus 5.6 and 5.6. Okay, so this is the value. Okay, and U1 and U2. Okay, Similarly, you have to find out the for the element 2 also. For the element 2, there is element 2 is located between the nodal point 2 and nodal point 3. Therefore, F2, F3. Okay, you have to A2, E2. For the element 2, the area is A2. For the element 2, the Young's modulus is E2. For the element 2, the length is L2. Okay, so that's why you have to A2, E2 by L2. 1 minus 1 minus 1 1, and element 2 is located between the nodal point 2 and nodal point 3. Therefore, U2, the displacement for the element 2 is U2 and U3. Okay, therefore F2, F3, that is equal to 600. Okay, 600 is nothing but area of the element 2 and into 200 into 10 power 3. Okay, that is Young's modulus, that is 200 into 10 power 3, and length for the element 2 is 400 mm. 1 minus 1 minus 1 1, and the displacement function for the element 2 is U2 and U3. Okay, now we have to solve these equations. Okay, solve this calculation. Finally, you have to find 1 into 10 power 5. Okay, that is 3 into 10 power 5. Okay, we have to keep outside 1 into 10 power 5 and multiply the 3 inside this matrix. Therefore, 3 minus 3 minus 3, 3 U2 and U3. Okay, finally you have to form the global finite element equation. Okay, you have to finally form the global finite element equation. Okay, you have to assemble that matrix. Okay, assemble the two elements. Okay, assemble the two elements into single finite element equation. Okay, therefore the total bar elements here, the total bar element is located between the nodal point 1, 2 and 3. The element 1 is located between nodal point 1 and 2. The element 2 is located between nodal point 2 and 3. Okay, therefore you have to assemble the matrix like this. You have to put 1, 2, 3 and 1, 2, 3. Okay, so for the element 1, see here, this is the element 1. There is 5.6 and minus 5.6 and 5 minus 5.6 and 5.6. Okay, that is between the 1, 2 and 1, 2. See here, this is the 1 and 2 and this is the 1, 2. You have to substitute the value here, 5.6 minus 5.6, and see here, second row you have to put this first column value minus 5.6, and second row you have to put the second column value, that is 5.6. Okay, then see this, the second element, for the second element, the finite element equation is this is F2, F3, 1 into 10 power 5, 3, 3 minus 3 minus 3, 3, and U2, U3. Okay, this 3 is located between this second row, second column, and this minus 3 is located between this second row, third column. Similarly, this minus 3 is located between the column third row, second column, and this 3 is located between the column third row, third column. Okay, so you have to apply here. Therefore, this 3 is second row, second column. So you have to substitute here, second row, second column. Okay, already is 5.6 plus 3, automatically can be 8.6. Okay, then minus 3, this minus 3 is located between second row, third column. This is the second row and this is the third column. That's why you are putting minus 3 here. Okay, and this minus 3 is third row, second column. This is the third row and this is the second column. Okay, so you have to put the minus 3 here. Okay, and this 3 is, okay, this 3 is located between the third row and third column. That's why you have to put the here, third row, third column, this value. Okay, so if okay, so this is the U1, U2, U3 for the global finite element equation. Okay, so now we have to apply the boundary conditions. Okay, see the sum. Okay, see the sum. At the nodal point 1 it's fixed and nodal point 3 it's fixed. Okay, once the nodal point 1 is fixed, means there should be no displacement at the nodal point 1, and also there is no displacement at the nodal point 3. Therefore 1 and 3, therefore 1 and 3, the displacement is equal to 0. 1 and 3, the nodal point 1 and 3, the displacement is equal to 0. Okay, therefore you have to apply here. Okay, displacement of the nodal point 1 and nodal point 3 are 0. Therefore U1 and U3 is equal to 0. Once nodal point U1 and U3 is 0, means you have to delete that first row, first column, and third row, third column. Why? Means there is no displacement at the nodal point 1 and nodal point 3. Therefore you have to delete this. Okay, therefore you have to delete this column, first row and first column, because nodal point 1 is, there is no displacement at the nodal point 1. Okay, that's why. And nodal point 3 is also no displacement, because that is fixed, the constraints are fixed. Therefore nodal point third row and third column is, you have to neglect this thing. Okay, finally, okay, and see here, there should be no forces acting at the nodal point 1 and nodal point 3. Therefore F1 is equal to 0 and F3 is equal to 0. F1 is equal to 0 and F3 is equal to 0. That's why you have to substitute here 0, 0. Okay. So 0, 0 you have to substitute here. Therefore, at the nodal point 2, the force 2 is acting. See here, at the nodal point 2, the force is acting. Okay, that is 200 kilonewton. Okay, that is 200 kilonewton force is acting here. Therefore, you have to 2 into 10 power 5. You have to convert in kilonewton to Newton means that is 2 into 10 power 5. Okay, is equal to, that's why you have to put in 2 into 10 power 5 here. So 2 into 10 power 5 is equal to 1 into 10 power 5 into 8.6. You have to multiply this 8.6 with this U2. Okay. Finally, you can get this value. Okay, 2 into 10 power 5 equal to 1 into 10 power 5 into 8.6 into U2. Finally, the displacement at the nodal point 2 is 0.2325 mm. Okay. So next you have to find out the stresses in the each element. Okay, if there's a two composite materials. Okay, the element 1 is another material, element 2 is another material, because the Young's modulus is varying for the element 1 and element 2. Okay, therefore the formula to find out the stresses is stress equal to E into du by dx. Okay, du is nothing but change in the displacement. Okay, with the original value, change in the displacement with the original length. Okay, this is the formula to find out the stress. Okay, so for the stress, sigma 1 is equal to, you have to took that element 1. Okay, plus element 1 is located between the nodal point u1 and 2. Okay, therefore the displacement of the nodal point 1 is u1 and then the displacement of the nodal point 2 is u2. Okay, for the element 1, the original length is L1. Okay, therefore 70 into 10 power 3, because the element 1 Young's modulus is 70 into 10 power 3 into 0.2325, because this is the displacement you have to find out from the sum. U2 minus 0 divided by original length of the element 1 is 300. Finally, you can get the value. The element 1 is 54.25 Newton per meter square. This is the stresses for the element 1. Okay. Similarly, for the element 2, so for the element, first stress for the element 2 is U2 into U3 minus U2 divided by L2. Okay, the Young's modulus for the element 2 is 210 power 3. For the displacement at the U3 is 0. Displacement at the nodal point 2 is 0.235. The length of the element 2 is 400. Finally, you can get the value. Sigma 2 is, stresses for the element 2 is minus 116.25. This minus is representing there should be a compressive stress is acting at the nodal point or at the stresses 2. Okay, for the element 2 there should be compressive stress is acting, at the element 1 there should be tensile stress is acting. Okay, so next one you have to find out the reaction force. Okay, the formula to find out the reaction force is R matrix is equal to stiffness matrix into displacement matrix minus force matrix. Okay, this is the formula to find out the reactional force. Okay, so you have to find, already know the reactional force is acting at the point nodal point 1 and nodal point 3. Okay, because there is no displacement between nodal point 1 and nodal point 3. Okay, therefore so reaction there is a total nodal point is R1, R2 and R3. Okay, therefore you have to, this is the final global stiffness matrix, 1 into 10 power 5 equal to minus 5.6 minus 5.6 0 minus 5.6 8.6 minus 3 0 minus 3 3. Okay, this is the displacement matrix, 0 0.235 2325 0 minus force matrix 0 2 into 10 power 5 and 0. Okay, so finally, so first you have to multiply this two matrix and you have to make them column. Okay, so this is the value, minus 1.302 2 and 0.69 minus 0.6975. Okay, so you have to subtract this matrix with this force matrix. Okay, therefore minus 1.302 minus 0 is, this is the value. Okay, and 0 and minus 0.6975. Okay, this is the value. This minus, you have to minus this value is this value. Okay, here 2 into 10 power 5 minus 2 into 10 power 5, automatically the two values are, this is a positive sign and this is a negative sign, automatically comes 0. Okay, so finally you have to find out the reactional force at the nodal point 1 is 1 minus 1.302 into 10 power 5 and the reactional force at the point is minus 0.6975. You have to add this two value. Okay, you have to add this two value, finally you can get the same value. What is the same value? That is the reactional force is always equal to your applied force value, applied load value. Okay, So this is the thing. Okay, the reactional force value. Reaction value is always equal to the applied load value. You have to add this two value 1.302 and minus 0.6975. It's almost similar, equal to this 2 into 10 power 5. Okay, so this is the one dimensional bar element. Thank you.